Hello everyone. So we are gonna solve, well, a lot of things rather, but one of the most um, trivial questions in graphs are from topological sort. I genuinely get a lot of problems while solving topological sort. So yeah, I think we can start with topological sort this time, and the goal of this is to get things going. So yeah, let's get right into it. We're gonna solve course schedule from now on. So 207 course schedule. Here we go. Right. So um, I will I will show you the question right now. But so but let me take a screenshot and we'll get to solving it. Right. Right. So here we go. Course schedule. Now, um, well, the question says the total of num courses. All right, and the total of num courses, and hold on a minute. Yep. Okay. Right. Here you go. So the total num courses. Okay. You have to take label from 0 to, well, num courses minus 1. Right. You are given an array prerequisites. Okay, we are given an array of prerequisites where prerequisites of I is equal to a of I and then b of I. That indicates that you must take course b of I if you want to take course a of I, right? So if you want to take course a of I, you need to take b of I, so b of I should be there first to go to a of I, right? Now, what is topological sort essentially is the question that we have. So uh, I would like to bring up something here. Topological sort. So let's read a bit about topological sort right now. There's this amazing website called, I think everyone should know it, that's USCO. So yeah, let's go through this website first. So it's USACO recommendation, and well, if you really take a look at it, we should read this together once. All right, so as you remember from our introductory lesson, blah blah blah. So basically this one is trying to explain what a cycle looks like. So this is like 0 to 5 and 7. This is a whole ass cycle over here. Similarly over here, 0 to 5 7, well, the only difference is directed graph needs to have it. If you had it like this, that's not a cycle. So if I were to ask you what a cycle is in directed graph, this is what it look like. Yes, there could be something like this, and so you might ask, is this a cycle? Well, it's not a cycle, because essentially the entire So, all the arrows should be pointing in singular direction, and it should come back to the same node. So start and ending node should be the same, right? That's like, I think, a pretty obvious thing, but nonetheless something to remember, right? uh, I think moving forward, so there is DAG, directed acyclic graph, both often found both in real life and computer science problem is called DAG. uh, well, it's just saying that you start from one vertex and you can never end up there. That's what DAG is. It's like an acyclic graph. There's no chance of having a cycle. So given topological sorting, right? So like the main essential part of topological sorting is DAG. Without that, there would be no topological sorting. So if you read through this, it says that a topological sorting is an ordering of the nodes in such a way that each arc given from node U to another node V, you will always appear before V in the ordering. That essentially means in a much more simpler terms, rather, the terminal, or basically the one node that starts with always, is dependent on out degree, right? Now what is out degree? um well, out degree and in degree, rather. So if in degree is 0, well, that's where a starting point is. So if you really look at this, there's no in degree over here. That's a 0. That's in 0 in degree. And it goes through multiple things, so on and so forth. uh, so one thing about topological sorting that's very very important, it's not necessarily unique, right? There could be multiple sortings for the same thing, for the same graph, and you should always remember this. Now, out degree, oh, by the way, so I had to explain what in degree and out degree is. This is in degree, this is out degree. Basically, the in a simpler layman terms, in degree is the number of paths coming into the nodes, or basically arrow coming into the nodes, and out degree is how many paths are being generated from your node, or being sent out from your node, or the arrows being sent out from your node. So that's in degree and out degree essentially. Now, right, now one thing about uh, you know topological sort is it can be done via BFS, it can be done via DFS. There are two ways to do topological sort, and well, I don't necessarily care about it, but I think from what I know that BFS algorithm for topological sort is nothing but Kant's algorithm. So this is something that's important. But rather than remembering the name, just remember this. It doesn't matter about the remaining of the names, but yeah. Oh, it does give an explanation here about integrity and non-degree. You can read it. I will provide the link in the description once the stream is done. So the question now is, in the topological sorting of DAG, right, what property related to degree does the first node in the ordering need to have? Well, like I said before, the out, so in degree should be 0, right? So if you really look at it, the in degree equal to 0 is it's quite literally the property that it should have. Because if you really think about it, if there is no nodes with in degree equal to 0, then yeah, you have a problem. Like that is definitely an acyclic graph. Sorry, that is definitely a cyclic graph, rather. So yeah, the sorting property is right here. Now this is the algorithm per se. So like find a node with in degree equal to 0 and position it the first in the topological sorting. Remove the node from the graph. What are you left with is also a DAG. So go back to step 1. Now um, instead of playing the animation, I think I'll just, let's just try to do a dry run rather. So let's pick up a rather simple DAG, and let's try this one, right? Because let's try this one, right? So there's 0, 5, 1, 4, 2, and 3. So if you look at this, there's nodes of 0 and so on and so forth. Now um, well, we first take a node with in degree equal to 0, right? Now the question could be, um, hey, like, which node do I pick up first if there are two in degree with 0, right? Like, look at this and look at this. Well, the simple answer is pick up the one that you get like, basically pick up the first one. It doesn't really matter, like I said, there's a reason why topological sorting cannot be unique and there could be multiple sorts, because you could start from here, you could start from here, right? So we'll start from here because, well, that's what animation will do as well. So like we'll start from here, 0 will come over here, so q will queue it into the 0 for now, right? This is the 0th node. Now let's assume once we get to 0, let's break it from the graph, right? So essentially 1 will have less in degree, so that will become 0. What's the next one? 2 will have less in degree, so that will become 1. That's nice. And 4 will have one more lesser in degree, so that will become 1, right? So you remove 0 and then now you have this, right? um, Now like, if you really look at it, you have 0 and you can make this -1 because we should not be picking it up again. uh, so that's that 0 1, and then again you have this, right? Now you have another two choices to make. What do I pick up first, 3 or 1, right? Well, I think I will go with 3. So actually, rather, that would be a smarter choice, is to have 0 and 3 into the queue. So once you have that, you take it out and you put 0 over here. Now you have 3, because the first two should be inside the queue. I'm sorry about that, I did not realize it. So like, like I said, I'm also learning it almost the first time. So yeah, um 0 and 3, right? So we'll start with 3, right? 3, or what does it break? Well, 2. So that seems to be a fair game. Oh, by the way, 1 will come over here, right? Because, well, you -1, and you have 1 over here, which will become -1. Now 2 will become 0, right? And 3 will go over here. So now 2 will become 0, so 2 will, well, come over here. Now you have 1 and 2. Um, right, -1, -1, -1. So let's start with 1. What does 1 break? 4 and 5. So 4 becomes 0 finally. 5 becomes 1. Right, and yeah. So the 4 comes into the picture. That becomes -1 again. Right, oh, 2 is -1 again, yeah. So 1 goes here. Let's go for 2 now. 2, what does it break? Well, only 5. So that's 0. And the 5 comes here, that becomes -1. So all the in degrees are done. 2 over, come over here. 4, well, interestingly there's nothing to break over here, so well, you want to keep the 4. And then 5 is also nothing. So you have your 0, 3, 1, 2, 4, 5 as a topological sort. Now this seems right to me, but again, you never know, right? Like let's see if we are correct, or rather if we were correct in our intuition. 0, okay, there you go. 3, yep. So you have your 0, you break it, yes. 1, that goes again in. 2, 1, nope, move on. So 3, 0, 3, okay, that's nice. 0, 3, 1, 2, 4, and lastly 5. There you go. So yeah, so this is how the topological sort looks like, right? If if you really think about it, it's like you could say the in degree keeps increasing in the, well, increasing order if you really want to think about it, or out degree keeps decreasing in decreasing order. So that's basically a topological sorting per se, right? uh, that's one way to think about it. And there's the DFS algorithm. At any point during the DFS traversal, we need to divide the nodes into three different groups, rather. Nodes that we finish visiting, that is off from stack. Nodes that are currently on the stack. Nodes that are yet to be discovered, right? Um, okay, so let's read through this ones because BFS seemed much simpler, but DFS is something that I have to read through as well. It's supposed to be that has not been reached to another B. If the graph is DAG, we can certain that B falls in category 1 or 3. B would be on the stack, then A, B plus. Okay, so if you read this, any node is popped from the stack after all its outgoing neighbors are popped. After all its outgoing neighbors are popped. That is such an important property. Okay, if you really read this, right? Let's suppose during a DFS we are in node A. So let's again, let's do some try run. Let's try to understand what they're saying. Let's say we are in node A that has an outgoing edge to another node B. Okay, if the graph is DAG, we can certain that B falls in category 1 or 3. Okay, it's node that we finish visiting, that is popped from the stack, or nodes that are yet to be discovered, right? Now if B was in stack, right, then the arc A or B would close the cycle, and this is impossible on a DAG, right? So here's the thing, right? Either the nodes are yet to be discovered, or either that you have finished visiting, right? If this is done, this should also mean that B, uh, B should have all its outgoing neighbors popped. So when I say outgoing neighbors, it could be like probably C and D. So these should be popped first, and that's when B can be popped, right? So essentially, the most, uh, or rather the most outgoing neighbor would be popped first and placed in the ordering. So it would be kind of a reverse order if you really look at it, right? So yeah. All right, give me a minute. did not even realize my mic wasn't on. Amazing. So, well, um, I think you did witness the entire dry run. Maybe not as much as I would have expected, but yeah. So like there's 4 and then 5. Oh, by the way, like whatever I did, right, that will be in reverse. So like it should be either reversed completely after you're done, or you could just basically append it in the first on the left side instead of right. That's up to you. So yeah, it seems like we have done the right thing. 0 2 and then 3. Yes, absolutely correct. That's amazing. So we basically understood the entire uh, topological sort, the PFS and the DFX. Like, so let's get back to um, you know other. Let's get back to doing D these things, the topological sort. So, well, we'll start with the curve, right? Uh, uh, um, right. So, well, let's start with the prerequisite. Let's start with the example. So, oh, by the way, let's keep this one thing very clear. Return true if you can finish all the courses. That means if we have a cycle, return false, else return true, right? Because we can complete all courses, we can make an entire topological sort if there's no cycle. It's all about, is there a cycle or not a cycle? That's all. That's what entire topological sort is. And it's basically if there is a DAG or not a DAG. That's essentially what a topological sort question boils down to, right? And how do we find that out? Using topological sort, that is using a cycle. You get the entire thing. So moving on, this number of courses is equal to 2, right? Okay, so this example 1, number of courses equal to 2, and then there's prerequisites, that's 1 of 0, right? Right. So how do you make a graph out of this is a question for us, right? Because essentially this will become you know 0 to 1, right? So um let's try to make a graph out of using prerequisites. Like let's have some examples. Like let's have a test case. Welcome to the test case section, I guess. Okay, I know I'm great. Shut up. So your test cases that could go probably. Oh, one thing to take care is number of courses. Yeah. So number of courses were like 10. I could have 0 10, and then I could have this and that, blah blah blah. So I could have 0 10, 1 2, 2 4, 4 6. So let's make a graph out of this, right? 1 to 10, so that would be 10 is 0, 2 to 1, that would be this, and there will be 4 to 2. Okay, that's interesting. And there will be 6 to 4. There you go. So well, that's how you could probably make graphs out of this. Now if I were to convert this part into the adjacent here is, how would it look like? Like uh, no rather this, how would that look like? So for 0 it would be nothing. However, for 10 it would mean 0 to be over here. Similarly for this is well, 2 is 1, so I think 2 could be 1, and 4 could be 2, and 6 could be 4. So these are your adjacency lists. What if there was like 3? What if there was something like 3 comma 2? So well, you do 1 comma 3, right? So the code for this should be pretty simple. For requisite in prerequisite, right? What I know is this will be the key, this will be the value, right? So well, there was like adjacency map. There you go. Right, and then you could say, like probably key comma value is equal to, or rather it's the opposite. I'm sorry. It would be value comma key is equal to requisite. So that is nothing but your 0 and then 10. If you people are able to catch up, 0 comma 10, because requisite over here is 0 comma 10, which is 0 comma 10, which essentially gives 0 comma 10 over here. I think this should be clear enough, I guess. So your adjacency map of key is equal to value, or rather not even equal to value. I'm sorry, let me dot append there you go. So you have your first code. This could be a function of adjacency mapper. There you go. Awesome. Boom. Right. So moving on, that's our adjacency mapper. Now coming to topological sort, right? What would be a topological sort function? Topo sort, right? Well, why do we need topo sort? We just need to check if graphs are acyclic or not, and let's implement a DFS function first. So like we could start with topological sort DFS, right? And then we also implement a BFS algorithm just so that we learn more, right? Of course, I could have just left it like that, and yeah, that would have been it. But what's the fun in that, right? All right. Anyways, this will be Topo sort DFS, right? So coming close to that, well, we'll start with for node, or rather for course in actually the better would be for node in number of courses, because remember, how am I able to get this is because if you really remember, like the constraint says that anything in prerequisites is still the num courses. So we know for the fact that the highest node in the num courses will be within the graph nodes. So this is something important, so that's why we have this. That That being said, um, well, we could start with this, right? So like we could have done DFS of node. Well, that seems fair enough for me. Now we'll have a implementer DFS that is super easy. Uh, you know, like we could have visited of, well, whatever the node, right? Visit of n is equal to true, and then we'll start with the for loop, right? You're like, hey, for u in adjacency map of whatever, like the n uh, if visited, if it's not visited, rather, if the visitor u is not visited, then do the like just dfs into this yet again, right? Dfs into u. Once you're back, then what do you do with it, right? Like, you basically run 0 and then you go to 1. Now what? We have to, we're keeping a visited node. That's nice. The goal is to get an array, right? This won't give us an array, but this will, right? So we need rather, I would say, answer. So, well, we could have an answer as a global variable, array, or a list rather. So answer dot append of, well, if you think about it, if everything is done, right? If there's nothing one or anything else, this will be skipped. The n will be a, so answer dot append of n. Awesome. So, well, essentially my answer will become 1 and then it becomes 0. There you go. It's basically a topological sort, right? And oh, by the way, so if you're doing this is important. If not visited of node, then yeah, go ahead and DFS. If it's visited, don't care, don't do it, and then just uh, well, I don't think you have to reverse the answer, but because um well, I don't think we have to reverse the answers. If there was like 0 and 10, right? 10 and 0. Nah, the opposite way. Okay, it's 10 and 0. Well, that would become 0 first and then 10 later, right? So do we have to reverse the answer? Well, I don't think so, because essentially, like, if you're doing this, like, hey, 10 0, well, start with this, and then you go down the line, the rabbit hole, and then you realize nothing, like, absolutely nothing. So you start with 1 over here, you're like, hey, nothing, yeah, that's weird. 1, that's not going. 2, that's 3 and 1, that's already visited. There's 3 and 2, so you'll have, hey, well, at least it's 2 and 3. And then you'll go for 4, which will be already visited, that'll be done, then it'll be 6. And then lastly, it'll be 10. That's all. That's all. Well, This gives us rather a sort, right? Mm, but how will we return the true or false? Because what if it was cyclic? What would happen if it was cyclic? Would we be able to tell that? Hmm, that's quite an interesting take. Well, this gives us the answer, but how do we really mm, think about it in terms of whether it was true or false? That's my question. Let's try an hypothesis to break out of this rut. So, what if it was 2, 4? Or rather, the second example would be nicer. You know, the 0, 1, 1, 0, and 0, 1. So, if we were to do the example 2, 1, 0 becomes 0, 1, and well, that will become this, right? So, if we were to do agency mapping, it will become 0 will become 1, and then 1 will become 0. Now, would our algorithm be able to catch it? Like, Topo sort, you do this, you start with 0. Now, it'll go for the 1, it'll push it into the answer, so you'll have, your 1 and 0. So, it will essentially put 1 first and then 0, which will be reversed, and it will become 0 and 1 because that was the starting point, right enough. So yeah, we have to reverse it first. That's a topological sort algorithm as such. So reverse the answer list. Yeah, but that will just give an answer. It will not give whether it was cyclic or non-cyclic. So our goal is to figure out how can we, like convert it into boolean rather. We start with 6, we start with 4. Let's assume, like, let's make a hypothesis to solve this, right? What is the main problem that we have to detect cycle via Topo sort, right? That's the problem statement, and the hypothesis is if, like, if we really think about it in very layman's term, if already visited and it's revisiting again, then it should be a cycle. Well, I think I can disprove this already. So, like, if there was like 0 1 2 and probably, like, right, 3. Okay, anything I do will actually end up leading to a cycle. If anything goes back to 0 is a cycle. Anything goes back to anything is a cycle, right? If you really look at it, right? Like, um, right, this could not be a cycle, right? So, like, if I do 2 or 3, this is not a cycle, because essentially I could have done, 1. I could have done, like 1, and then I've visited 1, that would be true. Have I visited 2? Probably not, but like, yeah, I would have done 2 true and then 3 true. Once I would have been done with 3, does it have outgoing edges? No, it'll go back. No, it'll just basically go back over here and then over here. Then 1 is 3, visited is 3, but that's definitely non-cyclic, but this is cyclic. So nope, that's wrong. hypothesis, right? But how do we really make sure? Mm, how do we think that there's uh, how can I say that this is a cycle, right? So, oh, okay. Okay. Let's assume, right? Like we'll give two different graphs, right? So there is 0, 1, 2, right? And then we'll do 3. Awesome, right? And then, and then we'll also do 0, 1, 2, 3, and yes, my bad. 3 and this. Okay, that seems fair enough, right? And I think this is where the recursion that the stack came into the to that amazing CS Academy website. This kind of makes sense now if I really look at it. So we'll start with 0, like um, this is visited 0, 1, 2, 3, 0, 1, 2, 3, right? 0 done, true. 1 done, true. 2 done, true, right? 3 done, true. We go back. Now here's the important part. We are having a stack for this, right? 0 done, we put it in. 1 done, we put it in again. 2 done, uh, again, and 3 done. Now once we start recursing back from here to 2, we'll pop it. We will pop the stack, and like you could have your answer. You're gonna put 3 over here, whatever, right? And then we'll recurse back to 2, right? And then we go back from 2 to 1, we'll pop it. 3, 2. That seems nice enough. Now this one, we will, well, not really recurse back to 1, but like uh, we'll keep it over here, because the loop will continue in the 1, right? Like the DFS loop. Hey, this is done. Well, we are back to 1. Now we'll go to 3. Is 3 already visited? Yes. Now what we'll check is, oh, rather than popping the stack right now, alright, okay, so if tree does not, if number does not exist in stack and is visited, it's not cyclic. Simple as that. You see this, you're like, hey, yeah, I'm done. 3 1 0, right? That's the hypothesis. Now coming to here, right? Like the same thing. We draw a visited array. Like 1 2 3 4 0 1 2 3. We start with 0, true. We start with 1, true, and then 2, which is again true, and then 3, that would be true. Now if you would have really given fucks, you'd been 0 1 2, and then 3, right? Well, the thing is, we pop out from stack when we fucking recurse back. Pop out from stack only when we recurse back. Right? So are we recursing back? No, we're going forward. We have put a for loop of 1, and then you see, hey, the 1 exists in stack and it's going here, then it's definitely a cycle. That's it. That is it. Now the question is, how do we make it into a code? Going back to this, you would realize that we should put up a x. My bad. What happened? Yeah, we should put up a stack over here for very good reasons, right? Visited node equals true. Yes. Stack dot push equals to n. I mean stack of push n. Once that's done, if everything is done, then we are just we're not gonna do this over here. We're not gonna append any answers over here anymore, right? Uh, Rather, we will just start going back, right? And then let's say we go from, let's say there was 0, DFS of 0. We are doing the 0 1 2 1 0 example, right? So we start with DFS of 0. Visitor of 0 is, well, true. Stack is 0, right? And we go to 0, you're like, hey, yes, 0 to 1, yeah, it's not visited, so we'll go to DFS of 1. And then you realize is 1 and 0 is there, so, well, if not visited will kick in, so this will skip. But if this kicks in, we have to check one thing, right? If this is not true, then elif is u in stack. If that's true, right, what we have to do is put up the cyclic equals to false for now, right? And what we're gonna do is something super simple. We keep it as cyclic equals to true, right? And once that's done, like, hey, cyclic is true, and we can just quite literally just return the function, and everything will just send over here, right? Like, if DFS 1 was gonna happen, nope, return. And yeah, there'll be cycles going on. Okay, we can also add a condition. If cyclic return, that's it. It'll keep breaking immediately, and yeah, it will in the end return this. It'll come over here. Now again put if cyclic over here, then just return false. Else in the end, if it doesn't work out, then return true. This seems like a bit of a mess, but I think we can cover it, right? Awesome. Let's get started, right? Hold on. So I'm gonna I'm gonna write this code myself first, and then we can do something about it, right? So I'll create a definition of mapper. That would be, well, what is it? Yeah, adjacency map is equal to this, and for request in prerequest, so you have for request and prerequisite, right? And okay, that took a lot of time, rather, but hey, at least we have something ready. Value key is equal to request, and then you have your adjacency map of key dot append of val. Oh, by the way, I think we should also have default dictionary with list over here. Yeah, so that should keep us sorted for now. Yeah, so mapping is done. Now, definition of diff is there's no right. Yeah, okay, that seems fair. If cyclic is true, then return true. Not that it matters, but the written value doesn't really matter. I could just return anything. It should have worked because our goal is to have a flag over here. So cyclic in general is just right. Cyclic in general is false, right? Then you have for you in adjacency map of no, yeah, okay. If not, in fact, if not visitor of whatever you, if visitor view is not done, then well, yeah, you could have done simple false into number of courses. That seems fair. If not visitor view, then DFS of you would make sense. And if it's visited, if that thing is visited, visitor view is false and false will become true. If that is true, yeah, okay, good. If you in stack, right, give it as stck, then well, make cyclic as true. There you go. And also just return true in the end, right? That seems fair enough. Yeah. Now, one thing that you have to keep in mind is visitor node is equal to true, and stack dot push for instance is node. So Python stack. Stack to append. Yeah, so that should be good enough. Okay, so stack is equal to dq also just to be safer. Collections input dq X DQ, return this thing, that thing. Right. And that in fact for I in num find range of num courses. Is it this? Oh, yeah. Find range of num courses. If uh if not visited I, then do DFS of I, and if cyclic is true, then just return false, right? Else you can just return true in the end. True because yeah, you get that right. If cyclist is true, then you have to return false, and you have to return true. I think this should work out well because we don't have to pop or some shit. We have to pop out. I don't think so, but that kind of makes no sense again. Wait, hold on. Do we ever have to pop out 0, 1, 2, 3? This will go 3, 2, 1. Let's say it finishes 3, right? It goes back and then it recurses back. There's nothing to recurse back to. 1, and if it's in 3, then that would be a problem. Right, okay. So every time we go back, we have to even pop it. So once the cycle is done, we also have to pop that thing. Stack the pop. Well, there you go. Okay. Yeah, I think it's safe enough to do this now. And we will start this. Yikes. Will be true. That's interesting. What is that? So we'll start with 1, 0, 0, 1, right? That will essentially make 1, 0 and then 0, 1, and then you do DFS node. God damn, I wish I had a debugger, god damn it. But hey, you can never go wrong with Visual Studio. Let me just open Visual Studio real fast. Hold on. Let's finish this up today. New folder, Leetcode, create, open. 207.py. Yeah. Command V. Class solution not needed. Definition can finish. Yes. Okay, where do I import the default from? This version. Default in Python. Yeah, from collections import default. Okay, got it. Import default. Yep. Prerequisites done. Right, can finish with number of courses would be 2, and then 1 comma 0 and then 0 comma 1. Right, let's start the debugger and run it. Alright, here we go. We have a debugger, right? So number course is 1001. You have your default dictionary. Okay, that's nice. False, false. Okay, that's correct. Stack is a DQ. Perfect. Sure. I didn't even invoke the mapper. It makes a lot of sense all of a sudden, you know. So the first thing first you do is you invoke a mapper. I know this could have been a much more cleaner code, but God forbid me. Alright, this is mapper. Here we go. Okay, prerequisite 1 of 0, key 0 value is 1. Nice. Other key is 1 value is 0. So if you look at it 0 1 1 0, so yeah, that's nice. That's absolutely nice. Okay, you have 0 1 1 0. Mapper is done. Number closest to the cyclic is false. And that's nice. Visited false false. Here's the df of I. That seems good enough. True df of u is equal to 1. Okay. Yeah. So that becomes true now. Like if you look at a stack as appended to 0 and then 1, right? Take a look. Cyclic is false here, but we have 0 and 1 in the stack. Now take a look at this. If you in adjacency map and that node is equal to 1, that means you have 0, right? There you go. Since it's already visited, now you're checking if it's in the stack. Is u and 0 in the stack? That's true, because 0 and 0 is here. So the cyclic will become true. It will return true. Well, there you go. And you pop it, right? You have your 1 and cyclic is what the fuck? Okay, that makes no sense. That makes no sense because we did cyclic also true, right? Ah shit. My god. My god. Okay, what is cyclic is unbound equals to what do you mean by cyclic is unbound? Cyclic no. Variable unbound Python. That's something new. I've never heard of this. That's bullshit. That makes no sense. The cyclic has already been assigned a value to it. What is this guy on? Cyclic, cyclic, cyclic. Yeah, that makes no sense. Huh. That's weird. I had no clue this was a thing, but apparently non-local cyclic is a thing. There you go. Yeah, okay. So yeah, I think this should work now. Cyclic, non-local cyclic. Cyclic is false for now. Yes, that seems right. Cyclic is true now. Right? The cyclic is true. Started pop. Cyclic is true, so it print false. There you go. Okay. Alright. I think this should be good for our, well, our question. But yeah, that could have been a much cleaner code here. This is what we're gonna do, right? Learning DS is not about cleaner. I mean, just finding the solution. It's to write a simple and cleaner code than before. So we're gonna improve on that a bit. Now, this should, in all essentiality, just run. Hmm. Well, I think this should work. Yeah. Boom. Awesome. Now, can we improve this code in some other sense? Well, I just like it to be like this, but yeah. So checking in stack is, well, O of n, and that's why it's pretty slow. But I think we can go further. All we have to do is, surprisingly, instead of having stack of dq, or even this rather, just have a recursion stack. There you go. This is not really a stack, but hey, who are we to judge? Um, so that becomes, well, stack of node equals true. It's in the stack. Now all we have to check if elif brother stack of view is true, then yeah, you have a problem here. Stack of view, then once that's done, you could do stack of view of equals to, yeah, false, and Yeah, this alone would increase the speed. That's interesting. Oh my bad. Stack of node. My bad. Stack of node equals false. Hmm. Let's see. There you go. Yeah, of course, this is not like the best thing, but if you like, really analyze complexity, it's of n plus e. That didn't do much difference. Right, that's one way to do it, and then there is BFS, which I think I'll continue in the next stream. Thank you guys for watching. This was definitely more of a session to understand for me. If you guys, think that you relate to me, that would be nice. Drop a comment or anything else if you want to. See you guys later. Bye bye.